As we move into the unit on sound, it's important for us to think about, well, what is sound? Well, sound is a wave. And sound is, more specifically, a longitudinal wave. This is where particle motion is parallel to the wave direction. We can also consider it a pressure or a compressional wave, right? It's going to have both compressions and rarefactions, and we'll get into that in a moment. It is a mechanical wave. Mechanical waves are determined by they must have a medium in which to travel through. So sound is energy that's traveling through a medium. Sound is traveling through air molecules. And sound waves propagate, right? They move circularly through a medium like air. Think about a bubble. So if this is a sound source, sound is literally moving away from you, much like that of a water wave. It's traveling in these circles, and a person who's an equal distance away from the sound will hear that sound at the same time and at the same volume. Sound waves travel at, well, let's just say a wide range of temperatures because they're temperature dependent. They vary based on temperature. And in class, we will study how the warmer the air, the faster the sound wave will travel. And waves are really just vibrations that come from your vocal cords. They generate sound waves. So the question that you can be thinking about is, can you hear sound in outer space where there's no air? And the answer to that is no, you cannot. Air is a mechanical wave, therefore it must have a medium. No medium, no sound. So the speed of sound in air. The speed of any wave depends on the medium through which the wave is traveling. At 45 degrees C, it travels at 358 meters per second, right? The speed of sound here. The speed of, and then at 21 degrees, it travels at about 344 meters per second. And at -1 degree C, it travels at about 330.4 meters per second. So the speed of sound in the air depends on the temperature. Sound travels faster in warm air than in cold. So we did a lab experiment in class. The temperature of the hallway was about 23 degrees C, which is 74 degrees Fahrenheit. And I asked you to calculate a couple things. If the temperature is 23 degrees C, we can actually calculate this. So this is the first time I'm walking you through this. So at 0 degrees C, its speed of sound is going to travel at about 331 meters per second. But the hallway wasn't 0 degrees, it was 23 degrees C. So we can calculate that. It's going to be 331 plus 0.6 meters per second per degree Celsius. So I can take 0.6 meters per second times 23 degrees C, and I get a value of, right, I can multiply these together, I get 13.8, I add that on, and we get about 345 meters per second, so roughly 345. So what was the speed of sound while traveling down the hallway based on the given temperature? Well, we would say it travels at about 345 meters per second. So we went and timed how long it took the sound wave to travel down the hallway, down and back. And then I asked you to find the distance. And each class was slightly off, but we could do that again and we could probably get closer to the actual value. So the hallway, sound reflection activity that we did, if we know that's 462 squares, each square is a foot, that's 462 feet. If I divide 462 by 3.28 feet per meter, I find out that it's 141 meters away. So based on the provided information, the speed of sound is 44.8 meters per second. The time it should have taken is 0.41 seconds. So it should have taken 0.82 seconds to travel down and reflect back. And that's what we hear as a reflected sound that we call an echo. So if we visualize a sound wave, right, we're back to this picture here. So if we have these people that are standing here, each person experiences the sound waves coming at them in the form of a compressional or a pressure wave at the same volume, the same frequency, and reach them at the same time. So let's look at the characteristics of a sound wave. As the vibrating speaker, right, this is an example of a speaker instead of a voice, as it moves forward, it pushes the air molecules, causing a compression. And as the string moves backwards, the more space is created for the air molecules to move, causing what's called a rarefaction. Air molecules move back to their rest position until the string comes forward again. So if I look at this slinky here, if I push it forward, the areas where we get these compressions, we call that just that. We call it compressions. We have a higher density of coils, right? When the first coil of the slinky is repeatedly vibrated back and forth, this is the disturbance that's created, which travels through the slinky from one end to the other. That's the disturbance. So we could graph this. We would call our crest the area of compressions, and we would call these troughs what we call rarefactions, would be the troughs. So we would get this compression, rarefaction trough, compression crest, rarefaction trough. And you could see that if we graphed it, we would have this very nice graph that we've been doing. These are called sine curves. So what oscillates in a sound wave? Well, air molecules is the medium that are oscillating parallel to the direction that the sound wave moves. This is the definition of a longitudinal wave. Sound waves are longitudinal waves. So remember that it's only energy that's traveling from one place to another. Sound waves are energy traveling through the air. So one air molecule moves from its rest position and then pushes on the nearest neighbors, causing them to move from the rest position. And that's what's transferring that information. See if I can get this to play. We're not going to listen to it all. You can watch this on your own.
Longitudinal wave. A wave is a disturbance of a medium which transports energy through the medium without permanently transporting matter. In a wave, particles of the medium are temporarily displaced and then return to their original position. There are a variety.
So I'm going to stop right there because you're going to want to come back and watch this. But I talk you through exactly what's taking place with the particles within the air itself. So I figured I might as well annoy you since I have you captivated here. So let's annoy you.
To allow you to find and hear and determine what the 5 most annoying sounds in the world are. You'll be sure to have to guess which is which. Here goes. First sound. Second sound. Third sound. And last sound.
So there you got a little bit of a taste of some annoying sounds, and we'll talk about what that means because they're really based on the frequency. All of those had a frequency in a very similar range. And therefore, we're going to be studying that the frequency is related to the pitch of a sound. So a high-pitched sound occurs at high frequencies. A low-pitched sound occurs at low frequencies. So a high frequency, remember, we have more oscillations per unit of time, and they have very small wavelengths. And here we have a low frequency, has a large wavelength, and a very, well, let's just say it takes more time to travel there. So we talk about frequency and energy. A low frequency is going to have low energy than something that has greater frequency. So we can look at a relationship. The greater the frequency, right, triple the frequency, you have triple the energy. So the relationship here is the greater the frequency, the greater the energy. And the same holds true with amplitude. A small amplitude is going to have low energy, where a large amplitude is going to have high energy. So the greater the frequency, the greater the energy, the greater the amplitude, the greater the energy. So pitch is directly related to sound frequency. And you're going to have a chance to find out your hearing range. And you can do that both on here, and we will also be doing that in a class lab. So what is the hearing range of the average human? Well, it's actually between 20 hertz and 15,000 hertz. But many of you can actually probably hear greater than 15,000 hertz. So dogs hear, right, dog whistles are very, very high frequencies, and we normally cannot hear them. And they can hear down to 50 hertz. Cats, even higher frequencies, and about the same. Bats can hear these high frequencies. It's not exactly known what their low end range is. And then elephants have a tremendously high range as well, just like bats. 100,000 hertz and even 5,000 for a minimum. So you'll find that animals, including humans, have a wide range of frequencies in which we can hear. And then we come to loudness. Loudness is measured in decibels. So what's the relationship between amplitude and energy? Well, the more energy, the more amplitude. If there's more energy is put into the string, or plucking a string, the string vibrates at a larger amplitude. The larger the amplitude produces louder sounds. And loudness is measured in what we call decibels. So this figure over here, we're looking at decibel values. So at these different values, notice the amplitude is increasing every 20 decibels. It increases tenfold, or 10 times. So the decibel scale is a measure of the amplitude of sound waves. We use the decibel scale because our ears hear a wide range of amplitudes. Every increase in 20 decibels, right, dB, means that the sound wave has 10 times a greater amplitude, and that's really kind of what I talked you through with this. And we'll be doing some calculations with that. So some common sounds and their loudness in decibels. So quiet sounds, right, 0, it's the quietest sound we can hear. We just put a 0 to that. But a whisper from about 3 feet away is about 10 to 15 decibels. Background sound level at a house is about 30 to 40. The noise in an average restaurant or our class is probably around 45 to 55 decibels. An ordinary conversation, although some of you have megaphone mouths, are probably closer to 70, 65, 70. City traffic, 70 decibels. A jackhammer cutting up a street 10 feet away has 90 decibels. iPod earphones turned to the maximum volume, 100 decibels. The front row of a rock concert or the front row of Stafford's classroom, about 110. And the threshold of pain from loudness. This is typically that can puncture your eardrum and your ear bleeds. This is about 120 decibels. We do not want to venture there. So how loud is too loud? Well, really there's this peak area in decibels that's really around 50 to 60 is actually the healthiest for the ear. It's a lot lower, but we have a tendency of straining our ears, and that leads to long-term breakdown of our actual ear itself. So dolphins, bats, and echolocation, or echolocation. Bats and dolphins, they use ultrasound waves instead of light to find their food. A bat or a dolphin's voice is like a sonic flashlight shining out a beam of sound. So you want to watch this video. It's kind of clever. They emit these short bursts of a sound. It's actually referred to as a chirp. When the sound reflects off their prey, they receive the echo of the returning wave. And the beat frequency is proportional to how far away the food is from the bat or the dolphin, right? These are predators. They're constantly finding their food. So both can determine where the food is by their brain by comparing the echo returning to the sound receivers or the ears on the bat. So there's kind of a basis of what we're going to be studying in terms of sound.